Today our topic is equipotential surfaces, which can be defined as family of surfaces that connects the points having same value of electric potential. Simply, equipotential surfaces can be defined as points on a surface have the same value of electric potential. It can be described in two forms, if in terms of electric charge and in terms of electric field. First we will see in terms of electric charge. Suppose we have an electric charge q naught and take a sphere at a radius of ra. As we know that this sphere is made up of the points having equal distance from the charge, then at any point on this sphere the potential will be same. Similarly, if we have another sphere at a radius rb, this one, then at any point on this sphere potential will be the same, and might be this will be equals to vb. But if they are equipotential surfaces, then their potential will be same. In other words, the potential difference will be zero. And here we will prove that at the same surface, the potential difference will be zero or same. At a distance Ra, potential Va can be given as kq over Ra, and at a distance Vb, potential can be given as kq over Rb. Then the difference of potential can be given as Vb minus Va, or putting values kq over Rb minus kq over Ra. Taking kq common, we have 1 over Rb minus 1 over Ra. But for equipotential surfaces, both points should have at the same radius, means Ra equals to Rb. By putting values, kq equals to 1 over Ra minus 1 over Ra cancel, and the change in potential equals to 0. It means that if we are taking 2 points at the same surface, then their difference will be 0, or in other words, both have the same potential. Similarly, if we have an electric field E, suppose this one, which are showing by horizontal lines from left to right, here we have some points, suppose this one, and this one, A, B, C, so on D. These points, when we connect all these points, we introducing a surface, and the potential at A, B, C and D have the same potential, or in other words, this line forms a equipotential surface. But if someone moves from point A to point B, then we are moving from one surface to another surface having a difference L of in means length segment, which means that here the potential difference will exist. But if you move someone from point B, this point, G, to F, so on G or H, now this forms another surface, or in other words, equipotential surface that have the same potential. Here we will prove that at the same surface the potential is the same. Suppose change in potential equals to, in the terms of electric field, E dot ds, and we are moving from if point A to point B, then change in potential equals to E ds cos theta, and as the angle between electric field, which is thiswards, and B, which is upward, having angle 90, which means that del V equals to minus A to B E ds cos 90, which is equals to 0, means del V or Vb minus Va equals to 0, or Vb equal Va, which means that if we move from point A to point B, the potential of A and B is equal, or potential difference is 0, as the same result. But if someone move from point A to point D, then what will happen? Here we will see the potential difference can be given as minus A to D E dot ds Then as here angle theta equals to 0, E ds cos 0 minus a to d. Here cos 0 equals to 1, we have minus a to d ds e equals to, here we will integrate and we will get L, this length. In other words, if we move from one surface to another surface, there will be exist a change in potential, and that is its change. We can also say that if we move from the same, if we move on the same surface, then the work done will be equals to 0. But if we move at the different surface from one surface to another surface, then the work done will be not equals to 0.